Let's just emphasize a few points about seeking predictability in rainfall then. So we talked about spatial coherence, and with the Indian example we said that the coherence seems to be large scale in space during the onset and withdrawal periods, whereas in the peak of the season here in July and August it seems to kind of be much smaller scale with many more north, south, east, west kind of patterns appearing here. You do that now, expand it to the tropics and do it. So now you're doing it from observations, the GPCP product, which is a mix of satellites and gauges, I think. It's also doing the same thing, 500 kilometers, 15-day running window. And you can see this is the coherence over the whole year, and this is for DJF, MAM, JJA, and SON. So you look at seasonal spatial coherences. And obviously you see some patterns here, but let's just zoom in. So for example, the ITCZ has these elongated type of coherences, zonal coherences, with these being more SPCZ, the South Pacific Convergence Zone and the South Atlantic Convergence Zone, whereas here it's much more spread out throughout, for example. And if you look at December, January, February, when the ITCZ is to the south here, this SPCZ is stronger, SACZ is stronger, and so on. You see certain patterns, but you still have the ITCZ kind of zonal coherence showing up here. If you compare that to let's say JJA in D here, so that's MAM, which has larger spatial coherence here than in JJA, and in general land regions have lesser spatial coherences than the ocean, which makes sense intuitively, that ocean provides this large scale boundary condition with constant supply of moisture, whereas on land you begin to get into orography, vegetation, soil moisture, sea breeze, land breeze, gravity waves, and so on and so forth. Okay, so that's also interesting that MAM, which is the transition season, actually has much larger spatial coherences here, all the way from the southern part into the Arabian Sea and Bay of Bengal, whereas it's much less so here in the rainy season of JJA. So let me see. Yeah, that's MAM. Not this one. Okay, this is SON. Okay, so ocean versus land is very critical to remember, and spatial dependence, seasonal dependence is very important to remember, and that shows up here as well. Looking at spatial averages of the mean autocorrelation in a 500 kilometer radius for land, coast, and open sea. So the area where mean rainfall over a sliding 15-day window is much less than 10 millimeter during the period shown in column 1 are not considered in spatial averages, so that's something to remember. Here columns 5 and 6 are pattern correlations between GPCP, which is one product, and CMAP, which is another product, and OLR is another indicator of convection and rainfall. So the point here is that the pattern correlations are high, so the conclusions here are not product dependent. With that, if you look at the correlations on these 500 kilometer radius, land in general is lower than the coast and the ocean, and there is a strong seasonal dependence. So you have higher correlation in DJF, which is the boreal winter month, lower in March, April, May, but actually higher than June, July, August, which is actually the minimum of the whole year, which is not very intuitive. Similarly in the coast and open seas. So open sea again, annual here, and December, January is the highest. Summer is the lowest, even though it's pretty close here. So open seas don't have as much, they have higher spatial coherences, or you can also think of it as mean autocorrelations, decorrelation scales. There's many ways to say it. So there is definitely land-ocean contrast. And The next figure is much more about looking at a seasonal evolution of these mean amounts in millimeters and spatial correlation of interannual ranks of amount in 500 kilometer radius. So again, ranking is done to keep it comparable as opposed to mean amounts. If you want to look at different regions, ranking them with the local maximum makes more sense than to use actual rainfall amounts. So these are spatially averaged over 12 tropical regions. I won't go through all of them, but again you will see the consistent picture we saw. These white panels are land and the gray panels are the ocean points. So you can see that, for example, Sahel and India both have the peak rainy season when the decorrelation scale or the coherence drops off, which we saw before. So the onset and the withdrawal have higher spatial coherences. So this has to be understood better, but somehow the monsoon trough moving or the ITCZ moving has a large scale dynamic associated with the onset, and the same with the withdrawal. But once the trough is set to the north at the foothill of the Himalayas, for example, the rainfall over the Indian region is much more spotty, popcorns popping everywhere based on the instabilities. So that kind of behavior you see basically at all rain points except these two are different. Let's see, F is the South Indonesian region, and the oceans on the other hand show in general coherence throughout the year, and they are not so seasonally dependent on the total amount of rain. Okay, here rainfall has a strong seasonality, but the the coherence doesn't have so much of a seasonality. So this is a CFI. Let's see which one this is. So F is South Indonesia, 10 south to equator, 90 to 120 degree east, and I is ITCZ, East Pacific. So you can see that its behavior is different as well, because it's in the high variability of the ITCZ, if you remember the structure of the ITCZ, pulled towards Central America and Gulf of Mexico, right? So nonetheless, these dynamics play into the whole idea of how rainfall weather within climate happens. And here I should mention that the high spatial coherence during DJF presumably can be dominated by things like the El Nino peaking in December, January, February. So even though monsoon seasons are in June, July, August here, and Sahel and India, so Sahel and India have June, July, August rainfall peaks, but they're affected by El Nino, which peaks in December, January, February. So that also affects the behavior over the Indonesian seas, where even though El Nino has a strong wind anomaly, for example, the local variability can actually act within it to produce weather that's more predictable. So the December, January, February if you look at F, the December, January, February coherence is low, whereas the summertime coherence is high, whereas December, January, February rainfall is high and coherence is low, and here rainfall is low and coherence is high. So actually it is consistent with what we are talking about before. Okay, so these kind of local regional dynamics make a difference. Just to kind of wrap it up, this is what we saw in terms of the ECMWF forecast, which I jumped actually. Sorry. So this is from the ECMWF forecast week 3 and 4, week 3 plus 4, important, to argue that it produces patterns similar to observations. Wow. You convince yourself, but it's not bad. And B here is week 3 to 3 plus 4 anomaly correlation of total precipitation for all year. So wherever the correlations are reasonable, about 0.5 or so, and especially in the Nino region, it's really high, up to 0.7 and above. There is high skill. So in general, week 3 to 4 in the tropics, ECMWF has regions where the forecast skill at week 3 to 4 is quite reasonable, and the basic behavior of the spatial coherence of rainfall in ECMWF looks reasonable compared to observations. So this is the anomaly correlation between forecast skill in weeks 3 plus 4 for different seasons. So we are again looking at DJF, MAM, JJA and SON, and again surprisingly JJA here is got very low correlation compared to DJF and MAM. So this is MAM. DJF, there is not much rain here anyways, but you can see that even in SON there is higher correlation than in JJA. But you can again see the dynamical structures like the ITCZ and the impact of El Nino here as well in terms of the high correlations here and related Walker cell perturbations and so on and so forth. So this is just to wrap up. This is the spatial averages of mean skill for weeks 3 plus 4 for all of tropics, land and coast. All tropics, not tremendously high correlation, especially explained variance can go really down with these kind of correlations even if they are statistically significant. But land is lower than the coast and the ocean, which is consistent with the idea of the signal to noise ratio itself. Even in the observations, the coherence, spatial coherence is higher in the coast and open seas compared to land. Hence, the forecast skills are also higher. But of course, we worry most about forecast skills on land. Okay, so this just gives you a sense of how we seek subseasonal forecast skills by looking for weather within climate. In other words, look for statistical properties like onset, withdrawal, rainfall intensity, spatial coherence, and see how they are modulated by climate. I didn't mention much here Madden-Julian oscillation and the so-called coupled Kelvin waves, coupled equatorial waves, which Rossby waves and Kelvin waves, also provide some predictability in many places, including over India and of course over Africa and Indonesia. And there are also differences in the wave properties and wave characteristics over the Atlantic versus the Indian and Indonesian seas, which also make that's CCEW, convectively coupled equatorial waves. They are called so because even though they have equatorial Kelvin wave properties, they propagate much slower than a free Kelvin wave. So that's why they are called convectively coupled, because we think they are slowed down by this convective coupling. But they also have a role to play in predictability at subseasonal timescales, which we will look at in more detail later on when we come back to Madden-Julian oscillations. Okay.